This time we're going to find power series like we've been doing, but we're going to do it using integration and approximation. Find the power series for natural log of x centered at 1. And of course, natural log of x can't be centered at 0 because the natural log of 0 doesn't exist. So it obviously is centered at 1. All right, well, the derivative of natural log, of course, as we know, is 1 over x. Now we can convert that into a power series. I can turn that geometric if I want to. If I'm clever, I can rewrite it like this. Let's see, x, it has to be centered at 1, so I know I need an x minus 1. But really, I want 1 minus r is what I want. And right now, that's not going to cut it. But what if I flip it around? What if I take that and I flip it around and I make it 1 minus x? That would still be centered at 1. Again, this is just a combination of creativity and experience on my part. Nothing more. The more you do this, the better at it you will get. Yeah, look at that. I've got 1 minus 1, which cancels. Negative times negative is plus x. So these two things are, in fact, equal to each other. But this one over here is ready to go. It's geometric. Term 1, of course, is the 1 up top. And the r is simply the 1 minus x in parentheses. So when I convert this 1 over x into a power series, obviously we're going to end with infinity. It's either going to be 0 or 1. I'm going to start with 1. If I need to change it to 0, I will. I'll just go 1 minus x to the n power. No, you know what? Term 1 needs to be 1, so I do want to start with a 0. I probably should have known that. Okay, so it's the summation from 0 to infinity of quantity 1 minus x to the n power. All right, that's great, but the problem itself didn't say find a power series for 1 over x. It said find a power series for natural log of x. So I need to take the integral of this thing. Now, there's two ways I can do that. I can just integrate the formula itself, or I can integrate term by term. I'll do both. If you integrate the formula itself, what's going to happen is it'll be 1 minus x to the n plus 1 power. You'll go up by a power. You'll divide by the new power. And oh, by the way, there would have been a u sub in there, so let me just throw another negative in front. If that's too fast, you can go back and just do it yourself and see that that is going to be correct. All right, so the power series for natural log will be that. Okay, so I can get rid of my 1 over x. That was just used to help me find what I have now, because 1 over x looked a little bit more geometric and I knew I'd be able to manipulate it. That's why I used the derivative. Interestingly enough, natural log of x on the laminated sheet, we know what the power series is. Let me just copy directly off of the laminated sheet. It's going to be x minus 1, and it doesn't say this on the sheet, but I'll put a 1 underneath it so you can sort of see the pattern forming, minus, signs alternate, x minus 1 squared over 2, plus x minus 1 quantity cubed over 3, minus, and then forever on. Just one more thing, because I know I've got some doubters here. Let's go ahead, like I said, plug the 0 in first. All right, so that's going to be the negative sign. 1 minus x to the first over 1. Plus, because sigma is sum. Let's plug a 1 in instead of a 0. Negative sign still out front. This will be 1 minus x to the second over 2. Plus, let's try a 2 in, then I'll make a 3 on the bottom. Negative sign still out there. 1 minus x to the third. I claim that black and green are the exact same things. Not everybody's going to agree with me, but you know what? I'm right. I love it. Here's why. You can see that if you distribute the negative into here, it will be x minus 1, so it's going to match. We already saw that. This negative, just like the subtraction, is still there. But you know what? 1 minus x being squared is the same as x minus 1 being squared because it's an even power. If you FOIL it out, either way, you're going to get x squared minus 2x plus 1 both times. And so the even powers don't matter. The odd powers, what happens is when you cube this out, you're going to have 1 minus x to the third, so there'll be 3 of them identical with a minus in front of it. If you flip all 3 of these around, you'd be the opposite of what you mean to be, but then here's the 4th negative to make it okay. So this is correct. The answer that I had in the box is a correct answer. And that's all they wanted. Find a power series for arctan of x. And of course that will be centered at 0, but they told you anyway. Again, arctan of x is on my laminated sheet. I'm not going to peek at it, even though you could totally peek at it. Instead, I'm just going to try it the way that I can do it from scratch. I know what the derivative of arctan is. It's the memorized formula from, I believe it was chapter 5. I think it's section 5.6. It's 1 over 1 plus x squared. Now remember, we're trying to get a power series for this. That's g of x. I didn't know what it was, so instead I'm making g prime of x, promising that I'm going to go back and integrate it to restore the problem back to g of x. But if you look at that g prime of x, it right now looks geometric already. I could very easily rewrite it in one more step to look completely geometric. There we go. Term 1 is this 1. The r is negative x squared. And by the way, the negative is not being squared, just the x is. All right, so if you convert that into a power series, you have this. So that looks pretty good. And of course, that 1 in front doesn't have to be there. I could just erase that. I think I will. And again, just to do what the book probably is going to do, I'm going to rewrite this one more time. As I mentioned before, a lot of times the publishers like to make things look like an alternating component is there. So they factor out, or move out, if you will, the negative 1 to the n power. So remember, there is a negative 1 here. So that's negative 1 to the n, and then it's x to the 2n. And that's how I've written it. That's going to be easier because when we end up going back to g of x, here in blue, remember g of x is what we're trying to get. That was arctan. We have to integrate this guy, and I think it'll be easier to integrate when you just have a 2n. That'll just be 2n plus 1. In fact, let's just do it. It's still a power series, but this time it's going to be x to the 2n plus 1. We have to divide by the new power, so there's going to be a 2n plus 1 in the denominator. And believe it or not, it's still going to be negative 1 to the n, not to the n plus 1. And the reason why is because we shifted over by one term, that plus c can take an effect. And so that's going to be it. I think I can prove this to you when you see me write it out term by term. By the way, that is the answer. That is correct. Well, I'm sure not everybody's convinced that I'm right yet. I have to prove that to you. All right, let's work this out term by term. If you throw a 0 in there, you get a 1 on the bottom. This is going to alternate signs, and it starts positively because negative 1 to the 0 is positive. X to the 0 plus 1 is just x to the first. Okay, great. Like I said, it's going to alternate signs. All right, so you get the idea. The denominator is going to go up by 2s. 1, 3, 5, 7, 9, 11, etc. Whatever the denominator is, the exponent on the numerator is going to be the same. So since this is 3 down there, that'll be x to the 3rd, x to the 5th, x to the 7th, etc. And ladies and gentlemen, this is exactly what's on your laminated sheet for arctan. It's exactly what I have. I'm sure I don't have this divided by 1. I probably don't have this 1. It just says x. but there's no factorials on the bottom. They're all odd numbers, and the sign alternates. So it works. Wow. Okay, so those are the book's examples. You can find power series, and sometimes you may have to integrate or take derivatives to get it to look geometric so that you can play with it and get the term 1 and to get the r, and then you just integrate it back so that it's back to the normal problem again. Fascinating. All right. Okay, number 3, we're asked to rewrite this function as a series, and then after doing so, we're going to find its interval of convergence. Well, first off, I feel like the best thing to do here would be to integrate both sides. I feel like we can make the right-hand side into some sort of a geometric look. So let's give it a shot. So I'm going to integrate them both. And we're going to integrate with respect to x, so I need a dx on each one. Okay, the right side, I need to do a simple but important u sub. So I'm going to make u 1 minus x. Du then becomes negative 1 dx, which we have right here. So that's the du. We have u, but it's to the negative second because it's in the denominator being squared. All right, now we can finish integrating that side. That's going to come out to negative u to the negative first, because again, up by a power, divide by the new power, plus c, which means that we have negative 1 over u, and again, u is 1 minus x. The plus c is really not going to affect the converging or diverging nature of this because it's a constant. And if we want to rewrite it as a series, the plus c can always be out front. So I'm going to ignore that plus c for now and just work with the fact that what we have made here on the right-hand side is geometric. Term 1 is negative 1. The common ratio is x. So I can simply write this term by term. Okay, term 1 is negative 1. If you keep multiplying by x each time, it's going to stay negative, and the exponent will just keep growing. Okay, so you get the idea. Eventually, we're going to land on minus x to the n when we get up to the last term. Unfortunately, this is not the answer. We wanted to write f of x as a series, not the integral. So I have to unintegrate, which is just a weird way of saying take the derivative. So we're going to do that now. I'll go term by term. If you take the derivative of the left-hand side, it's just going to become f of x. It's going to knock the integral off. If you take the derivative of the right-hand side, of course, negative 1 is 0. And you get negative 1 minus 2x minus 3x squared, etc. And so the generic term at the end is going to be minus n x to the n minus 1. And we can use that generic term to write this as a series. I'll do that up here. All right, we're going to go from, in this case, 1 to infinity. I'll show you why in a moment. The summand will be the formula that I just came up with. You can see that that works because if n is 1 and you plug a 1 in, that's going to give you negative 1 x to the 0, which would be negative 1. And indeed, that's what we started with down here in the green step. So that's why I want the index to be 1, not 0. All right, now we need to find the interval of convergence. So I'm going to give myself a little bit of room, and we'll try out the ratio test. And of course, the ratio test always starts out with the limit as n approaches infinity. Absolute value. The n's get replaced with n plus 1s. That's just going to be x to the n.
because it'll be x to the n plus 1 minus 1, so we're going to get some canceling. We'll divide by the original, so I'm just going to write it as I see it. And when we simplify, you can see that the negatives will cancel. Using L'Hopital or L'Hospital's rule, the n plus 1 over n will become a pair of 1s when we're out near infinity. And we just have one extra x in the numerator. So it's simply going to be the absolute value of x. And of course we want the interval of convergence, so that has to stay less than 1, meaning that unofficially x is going to be between 1 and negative 1. All right, so that's our unofficial answer. Now we have to test the endpoints to see what's happening there. All right, we'll start off with x being negative 1. If you put a negative 1 right in here where I'm up in the green equation, you're going to get negative n times negative 1 to the n minus 1. This will alternate, but it's just going to wildly go back and forth and oscillate. So this diverges. It's technically the nth term test, but that's going to diverge. If you put x equals positive 1 up there, you're going to get the negative sign, of course, and the n. And you'll have 1 to the n minus 1, which of course is just 1. And that's just going to grow. It's going to stay negative its whole life, but it's going to get farther and farther from 0. It will also diverge by the nth term test. And so actually, our unofficial answer is now officially correct. And of course, as always, you can write it in interval notation as well. It means the same thing. Both are fantastic. All right, onward. Number 4, without using your graphing calculator or any sort of technology, we want to figure out this definite integral, and we want to evaluate it with an error of less than 1/1000th. It's the arctan of x from 0 to 1/4. All right, I'm going to go ahead and take the derivative of this. Normally, taking the derivative would be a strange thing to do, but I happen to have the derivative of arctangent memorized. And I like the way it looks because I can make it look geometric pretty easily. Like so. So term 1 is going to be the 1 up top in the numerator, and the r is going to be negative x squared. All right, so if I write that out term by term, obviously it starts with a 1, and we're going to be multiplying by negative x squared every time, and so the signs will change. The exponents will increase by 2. You get the idea. But that's not what I wanted. The green stuff is well and good, but I took the derivative of black, and black is what I started with. So to get back to black, you actually have to integrate this, which isn't too hard to do. I'm going to integrate it. We'll go term by term with respect to x, of course. So imagine a little dx at the end here, differential. So the 1 becomes an x minus 1/3 x to the 3rd. The signs will continue to change, and you know that you're going to have x 1/5 x to the 5th minus 1/7 x to the 7th, and so on. Now, even though I integrated term by term, this, you may recognize, is the memorized formula for arctan. So when I changed from arctan to the green derivative, I integrated to get back to arctan. I still have to integrate the arctan. So I have to integrate this one more time. Hopefully that's not going to confuse people, but that's what we need to do. So again, I'll integrate term by term. So x becomes 1/2 x squared minus, and I think you can completely follow the rest, so I'll just work ahead, and hopefully you'll agree with me here. All right, that looks correct. If you're not sure, you can always take the derivative of each red term and make sure that you're back to the line above. And it is correct. All right, now we're going to integrate from 0 to 1/4. Again, I like to make the brackets on each side. Most teachers simply put a straight vertical line down the right and put the 0 and 1/4 there, and they don't put anything else. It's an old habit of mine. Old habits die hard. My calc teacher did that, and I have always done it myself. All right, so now we're ready to evaluate. So we're going to take the 1/4 and start plugging it in. Hopefully we're not going to have to use all of these. Remember, the error has to be less than 1/1000th, and then we'll be able to stop. And so I feel pretty good about this. We don't have to plug in the 0 because I think it's pretty clear to see that all the terms have x's, and so you're just going to end up with a bunch of zeros. So we won't need to do that. All right, let's start with the 1/2 x squared. That's going to be 1/2 1/4 squared, which is 1/16. Okay, so the first term is 1/32. Okay, so far, so good, but 1/32 is too big. It's not 1/1000th, so I need to keep moving. All right, minus the next one. We've got a 1/12. And then we have, okay, it's to the 4th power. Let's see. 1/4 to the 4th. Well, 1 to the 4th is 1. 4 to the 4th is going to be 256. And I think it's pretty clear to see that 12 times 256 is going to be well bigger than 1,000 there in the denominator. So we can thankfully neglect that term. We don't need it. And so our answer is simply going to be 1/32. That worked out really nicely. Now, of course, I'm a little curious to see if I'm right or not. So I'm going to go ahead and switch to the graphing calculator. I'm going to plug in my 1/32. We'll see what that is. And I'm also going to see what the arctan of x integrated from 0 to 1/4 comes out to be. I think I'll do that one first. So let's slide over to the graphing calculator. All right, let's see what this gives me. 0.0309 and 1/32, which was my answer, is very, very close. You can see that we are within 1/1000th. Both of them round off to 0.031, so we're there. So that's great. So that's number 4. All right, finally, last but not least, I want to clarify the wording that you might see in certain directions, either from myself or from standardized tests that you'll be taking. If you see a Taylor or Maclaurin polynomial, polynomials actually have ending points, 3rd degree, 4th degree. They don't go on forever, okay? If you see words like find, generate, give expansion, use the definition, you've got to show all your work, all the derivatives, plugging in the numbers. You develop it from scratch. Likewise, if you have a Taylor or Maclaurin series, the difference between a Taylor-Maclaurin series versus a polynomial is a series will go on forever. Typically, they're infinite for us. Again, if you see those same 4 phrases, find, generate, give the expansion, use the definition, you've got to build it from scratch. You've got to show all your work, the derivatives, give the formula, everything. Any power series that's geometric, immediately go to our trusted formula, term 1 over 1 minus r. That's a major shortcut. If you're asked to find intervals of convergence, remember that the endpoints don't have to be tested with a geometric. They're going to diverge all the time. And finally, last but not least, here at my number 4, if you see directions that say things like use the polynomial, use a known series or a memorized series, then you can use the memorized formulas. Generally, you're allowed to use them. More often than not, from what I've seen, College Board, if you have sine, cosine, and e to the x memorized, that's what you want. You don't want to build things from scratch. It's not wrong, and it's a huge time saver. So hopefully that clears things up a bit. All right, we've done 3 pretty intense days. Hopefully it made sense, and I'll catch you next time.